In this video, I'll be talking about our first lab, which examines constant velocity. The purpose of this experiment was to observe and analyze motion of an object at a constant velocity. Tracker will be used to find the position of the object at certain time intervals. A computational model will then be built using GlowScript that will predict the theoretical position of the object at certain time intervals using Newton's second law. The two models, real and theoretical, will then be plotted against each other and compared. Our results were that the predicted model of the position of the object over time was similar to the actual position of the object over time. The observed velocity was a bit larger than the expected velocity, with a percent error of 4.08%. The physical principles used were Newton's second law. In this experiment, the change in velocity was 0, meaning there's no net force from the surroundings, which was a whiteboard and the space around the marker, acting on the system, which was an expo marker. This equation can be manipulated to glean the position update and velocity update formulas listed here. These equations can be used for this experiment to update the velocity and position over small changes in time. They will be the basis of the computational model that will give us the expected results. Why are we using these physics principles? Newton's second law, and by extension, the position and velocity update formulas, is a powerful tool for predicting the future. In this lab, they will be used in the computational model to predict the future position and velocity of the marker over small increments of time. This prediction can be compared with the actual data from the observation to see the accuracy of our model as a whole. Okay, for tracker, a video was taken of an expo marker rolling across a whiteboard at a constant velocity. This video was then uploaded into tracker, where the video was analyzed to determine the marker's position over time. The expo marker, which was 0.14 meters in length, was used as a reference for distance. The coordinate system was placed with the origin at the start position of the marker. The marker's position was tracked along the x-axis of the coordinate system and by using its center of mass in each frame. Since the marker was moving from right to left, it was moving in the negative x direction, so the resulting slope is negative. Here is what tracker did. For the computational model, I first found the initial conditions needed for the model from the data gleaned from tracker. The initial position was negative 0.005 meters. The initial velocity was calculated and found to be negative 0.367 meters per second. The start time was 0 seconds. The end time was 1.3 seconds. The change in time was 0.033 seconds. The marker mass was 0.01 kilograms, and the net force was 0. The code worked by using a while loop to update the velocity and then the position of the theoretical marker over time increments of 0.033 seconds using the position update and velocity update formulas until the ending time. Here's the code I used. The initial conditions were changed within the code as stated in the previous slide. This code again uses a while loop to update the velocity of the marker using the velocity update formula and the position of the marker using the position update formula over increments of time, delta t, until the end time. The code creates a model of the position as well as graphs of position versus time and velocity versus time. When the code runs, here's what it does. Here are our results. The position versus time graphs are shown below with the observed in blue and the expected in orange. The expected slope was negative 0.367 while the observed slope was negative 3.82. The expected velocity was negative 0.367, the value we calculated earlier, but the observed velocity was negative 0.382, a value higher than we expected. The percent error was calculated below, and it is 4.08%. In this experiment, we found that the slope, which is the velocity of the observed model, followed closely the expected model, but not exactly. Why? The fundamental error is that it is likely that the observed data doesn't follow the expected data because the net force is not 0. This could be due to friction of the surface that we didn't account for. The deviation could also be due to human error. It's possible that the initial push was at a slight angle, and there could have also been tracker errors. Selection of the center of mass may not have been entirely accurate. What if the axes were flipped? If instead of defining the coordinate system as the x-axis and in the negative direction, I'd use the positive x direction, the slope of the position versus time graph would be positive instead of negative. In terms of physics, this means that the direction of the velocity would change. It would be positive, but the magnitude would remain the same. What does this mean? It is not possible to say how many pushes and pulls were added together to give 0 net force. There was frictional force to account for, but it is unknown what else could have affected the force due to lab constraints. However, we know that there was not actually zero net force acting on the marker because our observed model deviated from the expected model. Thank you.